All right, the next problem is the one that I've already done in terms of like how we do it, but let's just do it again because it does properly live in this section. And we're going to find vector, there's actually 14 in the section, and we're going to find vector, parametric, and symmetric equation for the line connecting P being -1 to -2 and Q being -3, 5, and 1. Okay, so we're going to start just from, we're going to connect them. Now there's actually, I've got a little trick for doing things like this sometimes. Okay, so the way that I've been teaching you to do this is to start here and go here. We can do that, but I've got another way to do it that I kind of think is kind of cool. So anytime you want to do a line, what we could do is we could say, you know what, it's going to be here at t equals 0, here at t equals 1. So what I'm going to do, I'm going to say -1 times, now I want it to be there at t equals 0. So what I'm going to do is I'm going to have 1 minus t there, okay, plus -3 t. Okay, so that's another way to sort of do it. Okay, so if you think about it, when t equals 0, this is 0, goes away, and you're just going to be left with -1. When t equals 1, this is 0, goes away, and you're left at -3. Okay. Similarly, your y of t is going to be 2 times 1 minus t plus 5t. Z of t is -2, 1 minus t plus 1 times t. And then I could write this as what? -1 plus 1 minus 3, so -2t. Let's write that as x of t, sorry. Let's also make that blue because that's our work. So in case you don't notice, I try to keep the sort of the explanations and the questions in black ink and the answers in blue. All right. Y of t is 2, and then what, plus 3t, just taking the -2t plus 5t. Z of t is -2 plus 2 plus 3t. Okay. So these are our parametric equations. It's going to be the same thing as if you just start here, right? And go from -1 to -3 is 2t. Oh, that should have been +2. Nope, -2, you're right. My bad. Okay. Start at 2 here. 2 to 5 is 3, so 3t. -2 to 1 is 3, so the -2 plus 3t. That would have been less work, but this approach has its advantages. So that's why I'm introducing it, because there will be times when this approach has its advantages. Okay? All right, your vector equation. Okay, well, that's not too hard. You don't really have to do much. You just take this as -1 to -2 plus t, -2, 3, 3. All right, so I just took the starting point again, okay, the t, and then this direction vector goes here, okay? So that's the vector equation. And then the symmetric equation, you just solve this for t. Okay, symmetric equations is going to be what? X plus 1 divided by -2 equals y minus 2 divided by 3 equals z plus 2 divided by 3. Okay? All I did, and all of those equal our parameter t, which you don't need that in a symmetric equation, but I'm just writing it out so that you can see where I got it from. Okay? All right. Next problem. Find a cone of intersection, or the curve of intersection This is number 29, incidentally. Find the curve of intersection as a vector function. Okay. Of the cone z equals square root of x squared plus y squared, and the plane z equals 1 plus y. Okay, so what we're trying to do, we're trying to find out where these two things are equal, of course. So let's set the two z's equal to each other. Square both sides. So we're taking here, because z equals the square root of x squared plus y squared on this cone, that's actually just the top half of a cone. Okay, so we're going to square both sides. And we're restricted to z being both of these being greater than or equal to 0. Okay, that's just this definition right here tells us that z has to be greater than or equal to 0. Okay, now we're going to solve this equation. Okay, we're going to solve and see what it gets us. Okay, so now the y squareds cancel, right? So we get, again, why am I doing this? Should be in blue. This I'm going to make in orange because it's not really work, but it sort of follows from that. Okay, so solving this, we get x squared equals 1 plus 2y, or we get y equals x squared over 2 minus 1/2. Okay, so now we're going to take and we're going to write this as a vector function. So let's make a parameter. So one of the things to think about, whenever I'm talking about a curve, curves are one-dimensional objects. And by one-dimensional objects, I mean one parameter. Okay, so curves have one parameter. Okay, so let's make x equal to t. Okay, if x equals t, y equals t squared over 2 minus 1/2. Z equals, well, look at z. Z is 1 plus y, right? Now, in order to check, I'd like to do a consistency check on this. Okay, so what I'm going to do is I'm going to check x squared plus y squared against 1 plus 2y plus y squared. Okay, I don't have to do that, but I could. Okay, I'm not going to do it because it's going to work out. Okay. Something is wrong here. Nope, everything's perfectly fine. Okay, I just had it here because I did it earlier, as in last year. And so when I join these together, I get 1/2 plus t squared over 2. Okay? So our r of t is t 1/2 t squared minus 1, 1/2 t squared plus 1. Okay? And you can check that this equality is satisfied. But we should know because it's already been sort of solved. Okay? All right. We're going to do another one of these. Don't worry. Next video.